All right, so this description of the two samples was brought up and used in our general discussion about comparing two population proportions. And so now we are ready to push forward and make this description here become an actual problem so that we can see directly the steps and further details of how we can compare the two population proportions. And so now I'm going to formally set out the first question regarding the description of the two samples we're having here. And this first question here is becoming our first problem. And we can use this as one example in continuation with the general discussion lecture that I delivered earlier. And so now, after looking at the description of the two samples here, now the question is asking at alpha equals 0.01. So recall for yourself this style of wording it, alpha equals 0.01. So alpha has, throughout this course here, has been understood as the significance level. So at alpha equals 0.01 are the samples showing strong evidence that there are less female drivers who favor a manual transmission. So there are less female drivers who favor a manual transmission. And the question itself are the samples, these two samples showing strong evidence. And so apparently, in a way how the question is worded, this problem brings us into the testing a hypothesis problem. So less female drivers who favor a manual transmission, but less female drivers, think a little further, less female drivers, less than what? Less than the male drivers. So basically this question right here, there are less female drivers who favor a manual transmission, means that after we have defined our lowercase letter p to be the proportion of drivers in general who favor driving a manual transmission, and also that we have discussed and decided that male drivers population is assigned the numerical label 1, and on the other hand, female drivers population is assigned with the numerical label 2. And so now in that way, there are less female drivers who favor a manual transmission. What I was in the middle of saying earlier is that now it means we are trying to prove that P2, this is proportion of female drivers who favor driving a manual transmission. We want to prove that P2 is less than P1. So P1 here is the proportion of drivers in the male drivers population who favor a manual transmission. And so now this is the comparison statements that we are testing, and it's the comparison statements about the two population proportions, P2 and P1. So this comparison statement here came straight out from the wording of our question that we have seen on the back on the computer screen, and it's an inequality. But now the idea is as follows. We will not directly test on a comparison statement like this, but instead we take a preliminary step as following. Algebraically, P1 less than P2 is equivalent to saying that P2 minus P1 is less than 0. That's one way to algebraically and logically re-express this inequality statement. And this way of how we algebraically re-express the statement here turn the inequality as another inequality where we're comparing a difference with 0. And alternatively, this same comparison statements we can also algebraically re-express that as P1 minus P2, but greater than 0. So we have, at this point, my bottom line here is that I have two different ways to re-express the same starting comparison statements here algebraically into these two inequality statements. And so now, in connection with what we did earlier, I have discussed in the general discussion lecture that there's a quantity that's the quantity dp is defined as p1 minus p2. So in that way, with this definition, which stays permanent, and regardless of whoever is playing in the role of p1 and in the role of p2, in that way that we have defined dp to be p1 minus p2, then let's have a look at this expression here. Even though, as I said earlier, we have two equivalent algebraic re-expression of this statement, but now we realize that p1 minus p2 greater than 0, this difference in this current inequality statement is consistent with our definition of dp. So we recognize that p1 minus p2 here is actually the dp, whereas here it's the opposite way around. And so I am now going to choose this specific statement right here to be regarded as the statements that I'm going to be directly testing with. So again, simply it is because the difference on the left hand side here is consistent with our definition of dp value. Alright, so from what it said right there, then since we specifically chose to work and test on this statement, and let's one more time rewrite that statement here, p1 minus p2 greater than 0. Now I want to see this statement as dp is greater than 0. And then further looking at this statement here that arrived at dp greater than 0, we recognize now that we have a statement that involves an inequality. So in that way, back to our first responsibility to identify the two hypotheses. Anytime we are doing a testing hypothesis problem, then this statement that we have just now recognized can be used in place of our alternative hypothesis. So now our alternative hypothesis H1 is saying that dp is greater than 0, and this is the hypothesis that we're proving right here. And so now in that same experience we have done for testing hypothesis on any value before, then no hypothesis this time can be recognized as dp equal 0. And so consequently, in that way, this problem, this testing hypothesis we're about to do in the same experience how we have learned through testing hypothesis, then when our alternative hypothesis has an inequality that points to the right hand side, the test we are about to perform is referred to as the right tail test. And so before I proceed any further, I have to make clear the one thing right here. If we now look back to the wording of the problem, the wording actually started out saying there are less females. We want to prove that there are less female drivers. So less than male drivers, of course, but there are less female drivers who favor a manual transmission. But now again, surprisingly, when it came to our H1, we actually turned that into a right tail test. And so what I need to be clear here is that anytime we're testing a hypothesis, comparing two population values, and specifically here we're comparing two population proportions, then just because the wording in the question saying less than doesn't mean that the alternative hypothesis has to be less than in here. It all depends on how we assign the numerical labels for our two populations. So it's simply because right from the beginning, right from start, when I was going over the general description, I set for that decision that I assign numerical label number 1 for the male drivers population, and And in that way, numerical label for the number 2 for the female driver's population. And that's how it resulted in our alternative hypothesis becoming the right tail test. So this exact same problem could have also been, and I repeat, this exact same problem could have also been a left tail test if the numerical labels for the two populations here were given the other way around from the beginning. So now, as a bottom line, getting a comparison problem into a right tail test or getting the same problem into a left tail test is entirely dependent on how we have assigned the numerical labels for our populations. And so anyone who is about to do a problem comparing the two population values, either population proportion values or population mean values, we just need to be ready as a skill, as essential skills of how to be able to run right tail and left tail tests so that we can be ready for any case that can happen. So it's not only because the wording here say less than that would make the problem become a left tail. Obviously, in this problem, it was a right tail because it was all depending on our decision for the numerical labeling in the beginning. And so now, after all that explanation, all that brief explanation, so now we know that we're proceeding into this test as a right tail test. I am going to start with the usual step here. I'm going to start out by accepting h sub 0. So I'm going to say if our null hypothesis h sub 0 was true. This is one way of expressing that. We're starting out by accepting that. And accepting h sub 0 to be true means we were accepting that dp equals 0. And so upon accepting this h sub 0 to be a truthful statement in stating this, then consequently, right out from the general discussion, I introduced the extended central limit theorem. So now, upon accepting h sub 0 to be the truth, then consequently it leads to the center of all dp hat value. So roll back to the earlier point of the video lesson where I introduced this to understand what that is. But now extended central limit theorem says mu dp hat we always equal dp. So now consequently mu dp hat in our case here, since we have accepted h sub 0 stating that dp equals 0, or in other words we accepted this value for dp, then consequently mu dp hat will equal 0. So this is the consequence based on the result we have seen or stated in the extended central limit theorem. And further, as a consequence, as I have said earlier when I briefly introduced the extended central limit theorem, then sigma dp hat value exists, but the actual calculation of the sigma dp hat value involves the two actual values of P1 and P2. So I'm going to say calculating this requires the actual P1 and P2. But we actually never knew these. And as a matter of fact, the entire problem here, we are only comparing the values. So we still don't need to know that, or in other words, we still don't have the actual values of any of these two, P1 and P2. So I know that sigma dp hat exists, but calculating it requires these two values. So instead of getting directly into the actual value of sigma dp hat, now as a next consequence, sigma dp hat can be approximated by the following calculation. I'm going to need a value so-called p hat c, a sample proportion combined, or a combined sample proportion. That's what the subscript c is, and I will explain what that p hat c is for. But once we have calculated this p hat c, I'm going to multiply that with 1 minus p hat c, And I'm going to multiply with another expression, 1 over n1. So now we recognize that n1 is the sample size corresponding to population 1 plus 1 over n2. And n2 here is the sample size corresponding to population 2. And this entire expression is put inside a square root. And so, again, I have to make it clear. This is not the actual calculation of the real sigma dp hat value, because I said earlier sigma dp hat value exists upon what we understand about the extended central limit theorem. But doing the actual calculation requires P1 and P2, the actual value of P1 and P2, which we never had. So calculation requires P1 and P2, and unfortunately we never had that. So we came up with an alternative solution. We approximate this value, and it has been working good enough that it's been many generations that statisticians have been working it this way. Any scientist, any researcher that's working testing a hypothesis comparing two population proportions, then they have been using this calculation as a close enough approximate for sigma dp hat value. So this is the formula to calculate the approximates for sigma dp hat value. Alright, so now let's spend some time to find out how we can calculate p hat c right here. So p hat c, as I said earlier, the subscript c right here means combined. So this p hat is a sample proportion. So allow me to use a name. We can think of this as a combined sample proportion. It's a combined sample proportion. And so here's how we're calculating it. For our specific problem right here, for our specific problem where we had the two samples given here, then p hat 1 was at sample size 450. And p hat 2, even though not required to be the same sample size, but p hat 2 was also at the sample size for 450. And so this is how I'm calculating my p hat c right here. My p hat c, the denominator of my p hat c is the total of the two sample sizes. So 450 from p hat 1 plus with 450 from p hat 2, and I put that as my total sample size, and that's why it's called combined. We are combining the two samples together. So the two samples total up their sample sizes to come up with this overall larger sample size. And so in that way, once we mix everybody together, once we have mixed everybody together and poured the two samples, combined the two samples together, then of course their successive count, 170 and 170 from the male driver sample and 100 from the female driver sample will be also mixed together and total up. So here in the numerator of my p hat c, I'm having 170 plus 100. And that is, ladies and gentlemen, how I calculate the p hat c value. So generally speaking, I mentioned a little bit earlier that the value on top of each of these proportion here is called the successive count. And so successive count is x1 from population 1. And successive count for population 2 is called x2. So this is x1 and that is x2. So the way how the formula was set up, that I was doing it, x1 plus x2 divided by the total of n1 plus n2. And this is how we set up p hat c in general. So normally how I approach the problem, I tend to lead my students or my viewers directly into getting it. And then when we're done, I'm going to restate the actual formula that ran behind the scene. And so this is the formula to calculate the combined sample proportion. So now back to this particular problem, our p hat c in this case is 270 over 900. Final calculation gave me a 0.3. So this is not p hat 1. neither p hat 2, but this is the combined p hat, the p hat that we obtained by totaling up the two samples and also totaling up the successive counts in the two samples and put them all together as a combined, as a pooled sample proportion. That's what the 0.3 is. So that means now we can proceed further to calculate that approximate, that good enough approximate of our sigma dp hat. So calculating further, we're looking at a square root expression where inside of that we're using 0.3 multiplied with 1 minus 0.3, and this product inside of the square root is multiplied further with 1 over 450 for sample size n1, and plus another 1 over 450 for sample size n2. And this is how we're going to calculate the approximate for our sigma dp hat. So my final calculation show that I have a 0.0306. So this calculation was initially a lot longer, but unless being specified otherwise throughout all of my video lectures regarding testing a hypothesis that compare two population proportions, then those approximates for sigma dp hats will always be rounded throughout my lectures in 4 decimal places. But again, I'm leaving that responsibility for viewers and my students to watch for each different rounding requirements in any of your problems that you are doing. So now in this particular problem I'm proceeding here, I'm now going to treat this value as an approximate to my sigma dp hat value. That means we have a close enough value for the average spread. So as a reminder again, from the extended central limit theorem, this value is our center because all of the dp hats values create a sampling distribution, a population, a distribution of data. And so this is our center of that distribution. And this is our average spread. That's why it's always important to calculate and to know these values. So we now have average spread. And so now in my next step, again, understanding from the extended central limit theorem that dp hat, even though written in lowercase letters, but understood as a random variable, a continuous random variable. And so further, we have known from the extended central limit theorem that dp hats would be, without any much worry about verification, normally distributed on a bell curve centering at this center right here, which is now currently accepted as 0. So I'm going to write 0 here for the center of our bell curve. And with sigma dp hat, which is now approximated as 0.0306. So I'm going to put a 0.0306 here for my average spread on this bell curve of all dp hats values. And so in that way, now we can imagine that we're having a bell curve. Any values and any of the values on this horizontal line being placed on this horizontal line is a value of the random variable dp hat. And this bell curve will have center right at 0. And average spread is our sigma dp hat being approximately, and now we can say that it's 0.0306 because we have already accepted that approximate as a good enough approximate to that sigma dp hat. So we can officially use that as our average spread on this bell curve right here. And so in that way, the reason I brought up this bell curve now is that on this given information regarding the two samples, then we have had one sample from population 1 and one sample from population 2. And so in that way, now we can recall that we define dp hats to be the difference between a sample proportion from population 1 minus a sample proportion from population 2. And that's why right here from what we already have, we can find, and this is our dp hats that we have, we can find the difference between our two samples that we're currently having. So 0.3778, I'm subtracting 0.2222. So this is our dp hat value, and it's only one among infinitely many other dp hat values out there. So final calculation of mine came out for this dp hat value to be 0.1556. And so now, upon realizing that we have a bell curve that represents our sampling distribution of all sampling differences in the two sample proportions, then our particular dp hat, being at value 0.1556, is somewhere on this bell curve. Of course, is one value on this bell curve, but now specifically it's a positive value. So now we know further that it must stay somewhere to the right hand side of the bell curve center here on this bell curve. And so just like how we were doing any other testing hypothesis, now there are a couple checkpoints. There are a couple checkpoints for consistencies here. So we have turned our testing hypothesis problem into a right-tail test because of our labeling, our numerical labeling decision from the beginning. But now, being a right-tail test, as we have consequently turned our problem into, then the sample itself, the sample value as the difference of the two sample proportions, stays on the right-hand side of the bell curve, and that's a checkpoint to check for consistency between our decision about the right test with how the value here becomes. And also, I must emphasize again that it's all due to the beginning decision where I assigned label 1 for population, for male drivers population, and label 2 for female drivers population. And that was the reason why this dp hat was found as p hat 1 minus p hat 2. So again, just like that, we always want, for any difference, either the difference in the two actual population proportion values, or the difference between any two samples, we always want the value from population 1 minus that similar value but from population 2. And that's how earlier when we were doing this calculation of the dp hats, we ended up with consequently a positive value. All right, and now on this bell curve, at this point everything is a consequence from accepting dp equals 0. And so now, upon realizing that we have a bell curve and our dp hat stays somewhere to the right hand side, now we have even though not the exact value of sigma dp hat, but we have a good enough that we now officially approve the approximate for sigma dp hat. So in this case here, on our bell curve, and specifically where our dp hat standing, we can calculate the z-score for our dp hat. So z-score for our dp hat is, and the way for calculating z-score is always the same, from where our value stands on the bell curve. In this case, our sampling difference as a sample. We're going to subtract the center of the current bell curve, which is 0 in this case, and I'm dividing by, even though not the exact sigma dp hat, but close enough. So I'm going to use that as the sigma dp hat value in the denominator. So 0.0306. So now I'm finding z-score of my particular sample value, the sample I have in hand here as the difference between our two sample proportions from the two populations. My calculation came out positive 5.08, and the actual calculation was a lot longer than this, but unless being specified otherwise, I have always rounded my z-scores to 2 decimal places. But again, it is it is viewers and my students' responsibility to watch for rounding requirements in any of your problem that you are doing. So the z-score here is positive and allow me to indicate that, to remind that to anyone by the red ink written here. So now another checkpoint for consistency. So our test was decided as a right tail test, all due to that beginning decision on the numerical labeling of our two populations. But now being a right tail test, look at our z-score. It turned into a positive z-score. And so now once we've had z-score, the next step now is to calculate the p-value of our current sample value here. So p-value in this right tail test is set up as the probability where among infinitely many values of dp hats, we're going to find the dp hats value greater than or equal 0.1556. And so now another checkpoint is for consistency is brought up again. Our test was decided to be a right tail test, was consequently driven into a right tail test. And so now when we're calculating the p-value for our sample, I was writing up with that right hand side inequality, or the inequality that points to the right hand side. And of course the value here in our inequality is always the actual value of the sample value that we have. And then this probability calculation is equivalent to the shaded area on the bell curve to the right hand side of wherever our dp hat can be. So if our dp hat known to be to the right hand side of 0, but wherever that can be on this right hand side of the bell curve center, this probability is the shaded area in black here, shaded to the right hand side of our particular dp hat value. And so now calculating this probability or this area on the bell curve, for anybody viewing this video at this point, it is just the same as getting the probability on the standard normal distribution bell curve, where we found a z-score greater than or equal to positive 5.08. And that again was the whole point of calculating z-score for any of our samples. And so for students in my class, I introduced the use of the LS&D program. And I have explained about what LS&D program is for many times in my earlier video lectures. So allow me to skip that explanation of what LS&D is and what it can do, or what kind of programs is equivalent to it. But now being a right tail area problem, I am going to run my LS&D program. And when it's asking for z-score, I will provide 5.08. But the answer of this LS&D program, as we want the right hand side or the area shaded to the right hand side of our current problem, this is a right tail test. And so I'm going to subtract the answer of LS&D from 1. And so that's how we come to our final p-value. So now on my LS&D program, written as a program to run with Microsoft Excel, then I'm going to go ahead and give or provide z-score 5.08 into this box right under that label z-score. And so the area to the left of this z-score on the standard normal distribution bell curve is supposedly this close to 1, so 0.99999 and a lot longer. So now back into my writing board, we need to do 1 minus that answer we have seen on the computer screen. And it's a lot longer. I wouldn't round any of these value yet because it's not my final p-value. Final calculation on something like this is 0.00002 and a lot longer. Be aware that some calculator express this lengthy decimal value with a lot of zeros in front, as a 2.0 e minus 7. It's just the way how calculators express a lengthy value like this as a scientific notation. But this value, if you ever see it, it means 0.0000006 zeros before the first non-zero digit here. But now this is our final p-value. So I am going to round that to 4 decimal places, which gives me a 0.0000 as usual, because I have always been expressing that throughout all of my video lectures. Anytime calculating a final p-value on the bell curve here, then unless being specified otherwise, I'll stick with the 4 decimal places rounding. But again, it is anyone's responsibility to watch for your own rounding requirements when it comes to doing your own problem. So now that we know that our final p-value was calculated to be 0.0000, so the next step, just like any other testing hypothesis problem, is to compare our final p-value, calculated p-value, with the significance level given in a problem. And we want to know whether this p-value we've had would fall below or would stay above the significance level given. And that's the question we want to know right for now. And so now back to the computer screen where it was having that description of the 2 samples and brought up as an actual testing hypothesis problem. Then I highlighted this earlier, and now let's highlight that again. But the start of this question is asking at significance level 0.001. So right here, this piece of information that I was highlighting here tells us that we now have significance level given as 0.01. And with a significance level given like this, then our p-value, our final calculated p-value, is directly shown to be below the significance level, as easily seen in the comparison here. And so now upon verifying that our p-value falls below the significance level, then that leads to deciding that our dp hat, as the only sample we have, is now an unlikely sample. We have only one sample, but in a way that we have accepted this dp hat to be equal to 0, then consequently it led to dp hat that we found, even though we found it so easily, but we found that dp hat to be an unlikely sample. It's not likely to happen at all. And so that leads to further saying that dp hat now is showing, or itself is, strong evidence. And having strong evidence here is for us to say that now h sub 0 must be rejected. So we are on one hand we are rejecting h sub 0. We can't accept dp equals 0. And as a matter of fact, we can also say dp hat is strong evidence for us to support. So rejecting h sub 0 means the same as supporting h1, the alternative hypothesis. So we first started out by accepting h sub 0, but now h sub 0 can't be accepted. We have to reject that. So we lean towards h1, the alternative hypothesis, saying that difference there between the two population proportions, even though we still don't know exactly what P1 and P2 is, but we know that their difference has to be, and we have strong evidence to prove that their difference should be above 0. It's a positive difference. And so one more time into the wording of the problem. Are the samples showing strong evidence? So we were looking for having strong evidence or not, according to the way how it's worded here. And the question is a yes or no question for the answer. And ultimately we showed that we had strong evidence. Our dp hat has been shown to have strong evidence. So in that way I'm answering yes, as the ultimate answer for this question. And now we are brought to question B of our current problem here. So right out from the same exact description of the two samples we've had and we've been working with throughout the lecture so far, then this particular question asks us to find a 99% confidence interval to estimate the difference dp. All right, so that's a couple highlights to catch regarding this question that we're about to do right here. And so right here in the wording and right from the highlighted information that I just pointed out here, then the question here is intended for us to calculate, to come up, to find a confidence interval. And so at this point, I have to mention that this video lesson, this general lecture that we are reviewing here is highly recommended to be viewed after you have already had, and I'm talking about the viewers or my students, after you have already learned about how to find a confidence interval in general. And so assuming that viewers arriving at this video lesson have already learned about how to find a confidence interval, then I can quickly remind about the following understanding. For any confidence interval, mainly to find it, and again CI is my shorthand writing for confidence interval. So for any confidence interval, to find it, we have to rely on a sample value. So we must find a sample value. And so a sample value here is a lot of time either given or purposely found by ourselves, the people who are working on the problem. So we must first have a sample value, and from where our obtained sample value is, we are going to add and subtract with the margin of error. And so again, this is the reason why I'm saying that this video lecture here is highly recommended to be viewed after you have learned about how to find a confidence interval, because all this concept here has been highlighted and specifically emphasized in the video lessons that introduced about the idea of finding a confidence interval. So here I can just remind that this E right here stands for, is the symbol for margin of error. That's why I'm writing that in red ink. And another highlight to remind, after you have viewed my other videos about to learn about how to find a confidence interval, is that confidence interval is always used to estimate a value. And so in our case here, let's look back at the wording in the problem right here. So now we want to estimate, we want to come up with the confidence interval to estimate the difference dp. And so this is the value that we want to estimate. And so dp we have already understood as the definition that we have seen earlier in the beginning of this lecture. Then dp is defined as the difference p1 minus p2. And this is the value now that we need to estimate. And so in that way, since we're estimating dp, then the corresponding sample value for dp is going to be our dp hat that we have already found. So now if we're looking back at our chart that we have sketched down earlier in the beginning of our lecture here, then P1 is the population proportion of male drivers who favor driving a manual transmission. And the similar here, P2 is that similar proportion, but in population 2, where I named that the female drivers population. And so we have already gave that we have previously given that definition dp to equal P1 minus P2. And so this is the value that we want to estimate using the confidence interval. But then corresponding to this dp value that we're attempting to estimate, then the sample value that I'm talking about, the sample value that we will be using to construct our confidence interval is this dp hat value. So dp hat value is the sample value corresponding to the value, the main population value that we are trying to estimate for. And so in that way, according to the given information we have already had here particularly, we already have for ourselves a sample value, which is the dp hat that we're having right here with value 0.1556. And so in that way, our final interval must look as following. From where the sample we have obtained, the sample value we have obtained, we are going to figure out the margin of error and add and subtract that from our obtained sample value. So this is ultimately what the final confidence interval of ours will look like. And even further, since we have already had the value for this dp hat, so I know for sure that at the end, where we finally come up with our confidence interval, then it should be taking 0.1556 as a center point, as a middle point in our interval, and add and subtract a margin of error. So now this is the main goal that we're looking for. So it looks like in this way right here, then we're almost done with our confidence interval, except for we need to figure out how big, how large that margin of error must be, in this case, for our desired confidence interval. And so really at this point, what I owe anyone viewing this video is an actual formula to calculate the margin of error for estimating the difference in the two population proportions here. So margin of error for our confidence interval to estimate dp is given by the following formula. E equals the z sub c multiplied with a square root expression, where inside of that we're doing p hat 1 for whoever is in place of p hat 1 times 1 minus p hat 1 divided by sample size decided on population 1, so n1. And still inside of that expression, we're looking at adding with another quotient, p hat 2, multiplied with 1 minus p hat 2, and dividing that by n2. So this is our formula to calculate the margin of error that estimates the value dp. And so now for this current formula, then the bigger part of this formula already contained all of those values we already had. So we have already had and listed down p hat 1, and in decimal it's 0.3778. We also had p hat 2 and listed down it's 0.2222. We had sample size for population 1 being n1 equals 450. We had sample size for population 2 listed here as 450, n2 equals 450. So in that way, we can almost complete this formula to calculate our desired margin of error. So we still haven't gotten to the z sub c, so now I'm going to leave that there, but at least the bigger part that is inside the square root here, I am going to have 0.3778 for p hat 1 in product with 1 minus 0.3778 for p hat 1, and I'm dividing that product by the sample size n1, 450. And I'm going to need to extend this a little further. And then still inside the square root here, I'm going to substitute in my p hat 2 value, so 0.2222 in product with 1 minus 0.2222, and that is to be divided by the sample size n2. So this is the bigger part, and it's ready for some calculation. So really what we need to know now is how to calculate the z sub c. And again, I emphasized earlier that this video lesson, this general lecture about comparing two population proportions is highly recommended to be viewed after you have already learned about how to find the confidence interval. Because back in those earlier videos when you have watched about finding confidence interval, you have seen and you have had some understanding about what the z sub c is. And so specifically the lowercase letter c as a subscript here, it is So this is a z-score relative, or the z-score corresponding to the given confidence level in our problem. So as a reminder, for this particular problem, our confidence level is given as, on the wording of the problem, we want to find a 99% confidence interval. So it's a confidence interval, but this percentage right here is indicating that we are looking at the confidence interval to be as highly successful as 99% confident. And so in that way, now I have a given, this is given information. I have a given confidence level being 99%. And so now, even though confidence levels a lot of time are expressed or given as a percentage like this in our problem, but when it actually gets into doing any real calculation with this confidence level, we will need to write it as a decimal. So I'm going to write this as a 0.99 in decimal for any calculation that later on uses this confidence level. So now let's find z sub c, and allow me to be a little skippy on the steps, because you have seen all the explanations of how to find the z sub c here back in the actual video lessons where I introduced the concept of finding inner confidence interval. So here, just first step here, it is going to be 0.5 plus half of our confidence level. So our confidence level in real-time decimal, 0.99, given in the problem. And so now I'm going to go 0.5 plus half of our confidence interval. Final calculation of mine showed 0.995. And this value right here, I call that, it's the left area. And so now moving on to step 2, I am going to use the program that I developed, or public viewers can also find a program over the web that serves the similar purpose right here. This program is going to take the left area that we have found and give out a z-score. And that z-score is now what we are looking for, the z sub c value. So finding z sub c is simply just a matter of running a program that takes this left area and produce the z-score and calculate out the z-score for us. So we're going to leave that completely for technology to handle. So my INV-Z program on the computer screen is here. So this time for the box right underneath the label left area, I am going to enter 0.995. And so the corresponding box where it's under the label Z right here is the z-score that the calculator have calculated for us. The program that I have developed calculated for us. And so unless being specified otherwise, usually my z sub c, for all z sub c throughout my lectures, I will be rounding to 3 decimal places. But it is viewers and students of mine's responsibility to find your own, to check for your own rounding requirements in any of the problem that you are finding z sub c values. So here it's 2.576. And the calculation, as you have seen on the computer screen earlier, was a lot longer. But as I said, I'm only rounding this to 3 decimal places. And so now we really are ready for our final calculation of the margin of error. So the margin of error here, z sub c, now can be substituted by 2.576. So 2.576. And that z sub c value must be multiplied with the lengthy expression here inside the root expression. So 0.3778 in product with 1 minus 0.3778. And it will take a little bit of patience to do this entire calculation in the calculator. Plus 0.2222 multiplied with 1 minus 0.2222, and dividing that by the other sample size N2, 450. And so now my final calculation for margin of error came out to be 0.0776. So the actual answer that came out from the calculator was a lot longer, but for this particular problem I rounded down to 4 decimal places. And so it is viewers or my students' responsibilities to watch for rounding requirements for each of your problem that you're working with. But now, so in the margin of error that we're doing here, then now our final confidence interval is ready. So what it says now is that at 99% confidence level, or at 99% successful level, we found the difference dp is anywhere up and down by 0.0776, up and down from this sampling difference between the two sample proportions that we have had. So 0.0776 up and down from where 0.1556 was. So this was our sample value, and this is the margin of error. So this is our final confidence interval. And so at 99% successful level guaranteed here, then the actual dp will be somewhere inside of this interval. And then again, we can always add this margin of error to the center point here, and the same thing as subtract this margin of error to the center point right here to create a low end and high end. So low end, after we subtract 0.0776 from 0.1556 here, we came to 0.078 for low end, and 0.2332 as our high end for this interval. And so the interval where it displays the complete low and high ends like this, we refer to this as the interval in traditional formats. And so I expect any of my students to be fluent with the two different ways of how we express our final confidence interval, either in the form of the center point up and down by the margin of error, or the interval that completely shows low and high, and we so-call the traditional format here. But once again, guarantee at 99% successful level over here, that difference dp is falling somewhere inside of this interval between the low and the high here. And so now that we have found our confidence interval that estimates dp according to the answer of question B we have just now answered. So our confidence interval to estimate dp in this case is the margin of error 0.0776, anywhere 0.0776 up and down from the sample value. Or in traditional format, we have found 0.078 and 0.2332 is the high in traditional format. Because it shows low and high. So from what we know at this point, our dp is, again as a reminder, our dp is known to be inside of this estimate at 99% successful level. So how is this result in part B that we have just now found connected to the result that we have done in part A, where I put them all in one problem? So in part A, it was a testing of a hypothesis. So the null hypothesis was stating that dp equals 0. The difference in the two proportions equals 0. And we had strong evidence at the end of the test. We had strong evidence to reject that dp here could not equal 0. And indeed, we started to support we lean toward supporting H1, saying that dp should be higher than 0 or being a positive value. And so again, we came to this right tail test simply because of our starting labeling convention from the beginning. And so, but in this way that we were going, in that way that we have already decided for our process to test the hypothesis, then at the end of part A, the only thing we knew was that dp is highly believed to be above 0. But now, how far above 0? Being above 0 by, is that only by a small amount, 0.05, or being a larger amount, 0.5, or being an even larger amount like 1 or 2? We did not know that answer at the end of part A, because the only thing H1 was stating is that dp was above 0. And so now this is how useful the answer in part B is given. It gives a better picture of where dp should fall into. So now at the end of part B, after we're looking back at that, after we're looking at part B and connect that with part A right here, then we can see that now this interval is completely a positive interval, and so we now know a better picture that our dp falls somewhere inside of this interval. So it gives us a better picture from the results we have proven in part A. And now, before we're completely finished with this current lecture, and specifically the current example that I brought up along with the lecture here, then let me make a couple important remarks here. So back to the two populations that we have isolated out. So here we're studying the male drivers population and the female drivers population. And so now, if we roll back to that beginning point where we were deciding to give the numerical labels for each one of these populations, then if the labeling decision was the other way around, meaning it's population 2 for male drivers and population 1 for the female drivers, then these are the consequences that will be brought to all of the problems that we have done. Obviously, this population now is regarded as population 2, and this female driver's population will now be regarded as population 1 if we decided the labeling convention the other way around, as indicated here. And so that proportion of male drivers who favor driving a manual transmission would now be referred as a P2. And similarly, now that same proportion of female drivers who favor driving a manual transmission would be regarded as P1. And so now, and then when it would come to sampling information, then the sample size from this population would be similarly or correspondingly N2 to be listed as 450 in the sample. And so the sample proportion we found there from that population 2 is now regarded as P hat 2, where it was 170 over 450. So the information itself won't change. It's just we change the subscript and the actual numerical labeling convention. That's it. And the sample size from population 1 would now be regarded as N1, which was equal to 450 as well. And the sample proportion from population 1 now would be regarded as P hat 1, being 100 out of 450. And the numerical calculation would remain the same, 0.3778 here for P hat 2, but 0.2222 for P hat 1. And that was the reason why throughout all of my steps, I keep mentioning that for whoever is playing in the role of P1 and whoever is playing in the role of P2, because here P, it's now different values that, it's a different value, it's the opposite value that's playing in the role of P hat 1, all due to that, the fact that we have switched our labeling convention. And P hat 2, and the different decimal value is playing in the role of P hat 2 right there. And so as a further impact for the entire work that we were doing, then the dp hat would consequently come out being negative 0.1556 instead of positive 0.1556 that we have seen back in the problem. Switching the labeling convention will not change our p hat c value, because the p hat c value simply just come out by totaling the two sample sizes. And I actually noticed a written error of mine from earlier. So sample size 450 from p hat 1 and sample size 450 again from p hat 2, and we go in 100 plus 170, and it would come out the same, being 270 over 900, which gives us a final piece of C, p hat c 0.3. So as I said, switching the numerical labeling from the beginning here did not change our p hat c over here. But now when it comes to testing our hypothesis in part A, then the two hypotheses would look as following. Again, as a reminder, it's all due to the fact that we have permanently defined dp to equal p1 minus p2, and again I have to say for whoever is in the role of p1 and whoever else is in the role of p2. So in this case, p1 is actually the population proportion from female drivers, and p2 is the population proportion from the male drivers population. And so in that way, algebraically, as a consequence, the alternative hypothesis H1 would say dp is a difference that's less than 0. And you can spend some time doing a little bit of algebra to see the reason why, very similar to how I argued that earlier in our video lecture when it was the original problem. And that would make our problem a left tail test. And of course, the difference dp will equal to 0 as always. And so in that case right there, the problem would be proceeded as a left tail test, where at some point when we need to bring all of our sampling dp hats value on the bell curve, the approximate for sigma dp hats remains the same, and the center of this bell curve, representing the entire sampling distribution of all dp hat values, would remain the same, with center at 0. But now from this center here, our sample value, the dp hats we currently have, would appear to be somewhere to the left hand side of the center on this bell curve. And so that means that consequently later on when we're calculating the area, it must be the area that's pointed to the left hand side, because it's a left tail test. And so in that way it will make perfect sense that calculating the p value for our sample will be proceeded or set up as the probability that on this bell curve we're going to find a dp hats being this time less than or equal to our sample value, which was already known to be negative 0.1556. And so consequently, as the next step, this area here on our current bell curve will equal to the area on the standard normal distribution bell curve, where we're looking for a z-score falling below negative 5.08. Because now, so recall that this z-score here was positive sign when our labeling convention here was the other way around. But now since we switched the labeling convention, this z-score will consequently become negative as well, along the way with how our sample became negative. Then the remaining final step for the calculation would become the same, and the final calculation should once again become a 0, 0, 0, which exactly agrees with the answer we have found originally throughout the work that I've done earlier. But so now at the end of the test, in part A right here, if we had the labeling convention the other way around as indicated here and proceeded as a left tail test, then all we knew at the end of the test was that dp in this definition here must be a difference that falls below 0 or being a negative difference. So in that case, when we advanced over to part B of our problem where we constructed the confidence interval, then the sample value that we need in the middle, in the center of our interval, is now a negative 0.1556. And from where that sample value is, we're going to be up and down by now changing the labeling, the numerical labeling here will not change our margin of error, and we can easily algebraically verify that, and so the margin of error would stay the same, being 0.0776. But then now if we actually put this interval, this final confidence interval, in the traditional format, we will understand a little better about that. So the low end this time would become the negative 0.2332, and the high end here, by adding this margin of error to the sample point, which is now currently a negative due to that switched numerical labeling, then the high end would become a negative 0.078. And so now if you can see that if the labeling, the numerical labeling from the beginning was done the other way around, then the interval would turn out completely the opposite interval, where you can see that it's completely a negative interval, and it's in the end it's still consistent with the result we have proven in part A. So that's the remark I would like to make right there. So it's really important that once anyone doing these problems has decided a labeling convention, then make sure you stay in that convention, and this is the way how we keep things organized. And so for a testing hypothesis problem in this way to become a left tail or a right tail, it's all going to come out not because the statement in the question was saying less than or greater than, but because of how we decided the labeling convention here. And then from there, as you can, if you can follow your work carefully, then the result will come out and be consistent with each other. And now at the end of this lesson, I'm going to quickly summarize a couple of formulas that we have learned here. So what's new in this? The new formula we have learned here is that we approximate the sigma dp hat, assuming you already understand what sigma dp hat is. Sigma dp hat can always be approximate throughout all of these testing hypotheses for comparing two population proportions. Then sigma dp hat can be approximated by the p hat c times 1 minus p hat c, and multiply with 1 over n1 plus 1 over n2. And the entire lengthy expression here is to be put inside of a square root. So that's one formula to be highlighted that we used earlier, and it will always be the same formula to be used again anytime we're comparing two population proportions, and given that they are independent samples. And the p hat c that we used here, we're going to just simply take successive count that existed in sample 1 plus that successive count that came out from sample 2. We total up those two successive counts, and we divide it by the total of the two sample sizes, n1 plus n2. So this is another formula that we have learned throughout the work earlier in part A of our example in continuation of the lecture. And at the end here, when it came down to estimating the actual dp, then the margin of error will be z sub c multiplied with the square root expression, where it has p hat 1 times 1 minus p hat 1 over sample size n1 plus p hat 2 times 1 minus p hat 2 inside of sample size n2, and all of that is again inside of the square root. And this is the formula to calculate the margin of error when we need to construct a confidence interval to estimate our DP. And as a reminder, so when we're looking back at the steps, if anyone can rewind this video to the earlier parts where I was showing the steps to find to calculate the z sub c. So z sub c is found the same way. In any other problems with z sub c. And what I mean here is that prior to this lecture over here, then we have seen other problems where we ask for confidence interval that require a z sub c calculation. So this way, how we're calculating z sub c now is done the same way of how it was done in earlier video lectures.